Hello there, and welcome to the Sleepy Scholar. Tonight's journey takes us into the vastness of space, to the shadowy world of black holes. We drift toward the quietest, deepest voids of the cosmos. Here, gravity itself has become an echo, a whisper so profound that it holds the starlight still. We journey toward those perfect shadows, the places where space and time curve into an infinite mystery. These are the final, majestic resting places of colossal stars, where the very fabric of reality bends in silent reverence. We will not approach too closely. We are safe observers, drifting by these ancient gravitational wells from a place of perfect calm. We are here simply to wonder at their nature, to understand the quiet power that shapes galaxies and pulls the starlight toward its center, not in violence, but in a final, peaceful embrace. If you enjoy these quiet explorations, I invite you to like, subscribe, or share a thought below. It helps other curious minds find a place to rest. But for now, get comfortable. Let your eyes grow heavy. Let's begin. Black holes are defined by their escape velocity. A black hole is not truly a hole, but an object of immense density. Its gravitational pull is so powerful that a point of no return is formed around it. To leave this boundary, an object would need to travel faster than the speed of light. Since nothing in the universe can achieve this, light itself, once it crosses this line, is held captive. This boundary is not a physical surface, but an invisible sphere of influence, a threshold where the laws of physics as we know them are pulled into a silent, inescapable waltz. It is the ultimate boundary where the universe quietly asks all things to stay. Albert Einstein's theories first predicted black holes. In 1915, his theory of general relativity described how gravity is not a force, but a curvature of space-time caused by mass and energy. Massive objects bend this fabric, and other objects follow the curves. Einstein's equations showed that if an object were dense enough, it could bend space-time so completely that it would essentially close in on itself, creating a region from which nothing could escape. This was a theoretical marvel, a mathematical shadow long before one was ever observed. It was the universe whispering of its own deepest possibilities, a place where gravity's power becomes absolute. The term black hole was coined in the 1960s. For decades, these strange objects were known by other names, such as dark stars or frozen stars. The mathematics described them, but the language to capture their essence was missing. It was the physicist John Archibald Wheeler who, in 1967, popularized the name black hole during a lecture. The name was simple, evocative, and captured the public imagination. It gave a title to the shadow, a name to the void, and in doing so, transformed a complex mathematical curiosity into a majestic and tangible concept for all humankind to wonder at. Stellar mass black holes are born from dying stars. When a truly massive star, many times the size of our own sun, exhausts its nuclear fuel, it can no longer support its own immense weight. The core collapses catastrophically under its own gravity, triggering a massive explosion known as a supernova. This event casts the star's outer layers into space, seeding the cosmos with heavy elements, but the dense core continues to collapse inward past all known limits until it forms a stellar mass black hole. It is a phoenix rising from the ashes, a star's final grand transformation into a quiet monument of gravity. Supermassive black holes live at the center of galaxies. These are the titans of the cosmos, objects with masses millions or even billions of times greater than our sun. Nearly every large galaxy, including our own Milky Way, is believed to harbor one of these giants in its core. They are not destroyers, but anchors. Their immense gravitational influence acts as a central pivot point, a calm eye in the swirling storm of stars, dust, and planets that compose the galaxy. They are the silent, unseen hearts around which the grand spiral arms of the cosmos quietly turn. Our galaxy's central black hole is named Sagittarius, a star. Located about 27,000 light-years away, hidden behind dense clouds of dust and gas, lies the tranquil heart of the Milky Way. We cannot see it directly, but we observe its presence by watching the stars closest to it. These stars orbit the unseen object at incredible speeds, some completing a full journey in just a few years. Their dance is a gravitational ballet, a testament to the immense quiet mass that holds them in its sway. Sagittarius A star is our galaxy's own gentle giant, a dark, sleeping shepherd for 1 trillion stars. The event horizon is the point of no return. This is the boundary of the black hole, the invisible line in space-time. To an observer far away, it would simply look like a perfect black sphere. As an object approaches it, time itself would appear to slow down, the object seeming to freeze at the edge for eternity. But for the object itself, time would pass normally as it crosses the threshold, unaware of the exact moment it has passed beyond the veil. The event horizon is not a wall, but a gentle, one-way door into the heart of mystery. A singularity is the theoretical center of a black hole. According to our current understanding, all the mass that falls into a black hole is crushed into an infinitely small point at its very center. This is the singularity, a place where density and gravity become infinite, and the known laws of physics and time cease to function. It is a concept that stretches our imagination to its breaking point, a place where the fabric of the universe is no longer just curved, but torn. It remains one of physics' greatest enigmas, a final silent point at the end of gravity's long story. Tidal forces near a black hole cause spaghettification. As an object, like a star or a person, falls toward a black hole, the gravitational pull on the part of the object closer to the black hole is significantly stronger than the pull on the part farther away. This difference in gravitational force, known as a tidal force, would stretch the object vertically while compressing it horizontally. This process, colorfully named spaghettification, would gently pull any matter apart into a thin stream of atoms before it even reached the event horizon. It is the ultimate quiet disassembly, a return to the fundamental dust of the cosmos. Black holes are seen by their effect on their surroundings. Because they trap all light, a black hole itself is perfectly invisible, a patch of black against the black of space. We find them by watching their gravitational influence on nearby stars, or more dramatically, by observing their accretion disks. As gas and dust spiral into the black hole, they accelerate to near light speed, colliding and heating up to millions of degrees. This superheated material shines brightly in X-rays and other wavelengths, forming a brilliant, glowing disk that silhouettes the dark shadow of the event horizon, a halo of light betraying the darkness within. Black holes are not eternal due to Hawking radiation. The physicist Stephen Hawking proposed that black holes are not completely black. Due to quantum effects near the event horizon, pairs of virtual particles are constantly popping into and out of existence. Occasionally, one particle falls into the black hole, while the other escapes, carrying away a tiny amount of the black hole's mass and energy. This slow, steady leak is known as Hawking radiation. Over unfathomable timescales, trillions upon trillions of years, this process will cause a black hole to slowly evaporate until it finally fades away in a quiet whisper of light. Time slows down near a black hole. Einstein's theory of general relativity tells us that strong gravity warps time itself. For an observer near the massive gravitational pull of a black hole, time would pass more slowly than for an observer far away. If one person were to orbit a black hole for a short period and then return to Earth, they would find that thousands of years had passed for everyone they once knew. It is the universe's own form of time travel, a place where a moment can be stretched into an eon, held gently in the grip of gravity. Black holes bend the path of light. The immense gravity of a black hole curves space-time so profoundly that even light, which travels in a straight line, must follow these curves. If a black hole passes between us and a distant star, the star's light will be bent around the black hole, a phenomenon called gravitational lensing. This can make the distant star appear in multiple places at once, or be distorted into a ring or an arc. The black hole acts as a cosmic magnifying glass, revealing its invisible presence by the way it quietly warps the starlight passing by. The first image of a black hole was captured in 2019, using a network of telescopes spread across the entire globe, effectively creating an Earth-sized observatory called the Event Horizon Telescope. Scientists were able to finally capture a direct image. The target was the supermassive black hole at the center of the M87 galaxy, 55 million light-years away. The image revealed not the black hole itself, but its shadow, a perfect circle of darkness silhouetted against the glowing superheated gas of its accretion disk. It was a monumental human achievement, a first glimpse into the face of the void. Intermediate mass black holes are a cosmic mystery. We have abundant evidence for small, stellar mass black holes and for supermassive giants. But the existence of black holes in the middle range, those with masses between 100 and 100,000 times that of our Sun, remains elusive. These missing links are crucial to understanding how the supermassive black holes grew so large. Their discovery would fill a vast gap in our cosmic story. Scientists search for them in the hearts of smaller dwarf galaxies, hunting for the quiet middle children of the gravitational family. Black holes do not suck things in. A common misconception is that black holes are cosmic vacuum cleaners, actively pulling in everything around them. In truth, a black hole's gravity is just like any other objects, and it only affects things that come very close to it. If our Sun were to be instantly replaced by a black hole of the same mass, the Earth and all the other planets would not be pulled in. They would continue to orbit the new black hole perfectly, held in the same gentle gravitational embrace, though our world would be plunged into a cold and endless night. The information paradox questions what happens to lost information. Quantum mechanics states that information about an object can never be truly destroyed, but a black hole, by its very nature, seems to destroy the information of everything that falls into it, leaving behind only mass, charge, and spin. When the black hole evaporates via Hawking radiation, that information appears to be lost forever, a violation of a fundamental physical law. This puzzle, the black hole information paradox, sits at the boundary of physics. It suggests that our understanding of gravity and quantum mechanics is not yet complete, and a deeper, more elegant truth still waits to be found. Primordial black holes may have formed at the dawn of time. Not all black holes may come from stars. Some theories suggest that in the very first moments after the Big Bang, the universe was incredibly dense and lumpy. In some of these overly dense regions, the pressure and gravity could have been so extreme that they collapsed directly into black holes. These primordial black holes could be of any size, from microscopic to thousands of times the mass of our Sun. They would be ancient relics from the birth of the cosmos, tiny seeds of gravity wandering the universe for all time. Cygnus X1 was the first object widely accepted as a black hole. Discovered in 1964 as a powerful source of X-rays, Cygnus X1 is a binary system, a celestial dance between two objects. One is a massive blue supergiant star, and the other is an unseen compact companion. By observing the star's orbit, astronomers calculated that its invisible partner must be incredibly massive, yet incredibly small, far too dense to be a normal star. It was the first strong observational evidence that black holes were not just theoretical oddities, but real and present objects in our own galaxy. A silent, powerful neighbor in the cosmic dark. Black holes help shape the galaxies we see today. The supermassive black holes at the centers of galaxies are not just passive anchors. As they feed on gas and dust, their accretion disks can blast out colossal jets of energy and radiation, powerful enough to be seen from across the universe. These jets heat up the surrounding gas, which can blow away the material needed to form new stars. This process helps to regulate the growth of the galaxy, determining how large it can become. The black hole acts as a cosmic gardener, gently pruning the galaxy and shaping its final beautiful structure. Quasars are powered by supermassive black holes. In the early active universe, some galactic centers blazed with a light that outshone their entire host galaxies. These are quasars, the most luminous objects in the cosmos. Their engine is not starlight, but a supermassive black hole in a state of rapid feeding. As vast clouds of gas spiral into the black hole's accretion disk, the intense friction and gravitational pressure heat the material to billions of degrees, causing it to radiate a torrent of energy across the entire electromagnetic spectrum. A quasar is the brilliant, radiant cry of a galaxy's heart, a beacon lit by gravity's feast, shining across the dawn of time. Spinning black holes have an ergosphere, while a non-spinning black hole is perfectly spherical. A spinning one, known as a Kerr black hole, bulges at its equator. This rotation twists the fabric of space-time around it, creating a region called the ergosphere, just outside the event horizon. Within this region, space-time itself is dragged along with the black hole's spin, faster than the speed of light. An object could theoretically enter the ergosphere and still escape, but it could not stand still. It is forced to join the cosmic waltz, caught in a gravitational whirlpool that turns with the quiet, relentless power of the black hole's own momentum. Energy can be extracted from a spinning black hole. The rotational energy of a spinning black hole is immense. The physicist Roger Penrose theorized a way to tap into it, now called the Penrose process. By dropping an object into the ergosphere and allowing it to split in two, one fragment could be allowed to fall into the black hole, while the other escapes. If timed correctly, the escaping fragment would fly out with more energy than the original object had, having stolen a tiny fraction of the black hole's spin. It is a way of pulling power from the void itself, a cosmic sleight of hand played with the laws of gravity. The no-hair theorem describes a black hole's simplicity. Despite the complex and massive stars they are born from, black holes are incredibly simple objects. The no-hair theorem states that once a black hole settles into a stable state, it can be described by only three properties: its mass, its electric charge, and its angular momentum, or spin. All other details of the matter that formed it, its chemical composition, its texture, its shape, are lost forever behind the event horizon. The black hole is a perfect, clean slate, a gravitational memory that has retained only the most fundamental outlines of what it once was. White holes are the theoretical opposite of black holes. The mathematics of general relativity are symmetrical, and they allow for a fascinating possibility known as a white hole. While a black hole is a region you can only enter and never leave, a white hole would be a region you can only leave and never enter. It would be a source, a place where matter and light are spontaneously gushing out from a central point. We have never observed such an object, and they are considered physically unlikely to exist. They remain a beautiful mathematical echo, a what-if whispered by the laws of physics, a fountain of light to balance the drain of darkness. Black holes are connected to the idea of wormholes. Einstein's theories also allow for the possibility of tunnels through spacetime, known as Einstein-Rosen bridges, or more famously, wormholes. In theory, a black hole could act as the entrance to such a tunnel, which would then connect to a white hole somewhere else in the cosmos, or perhaps even in another universe entirely. However, these theoretical bridges are understood to be incredibly unstable. They would likely collapse the instant anything tried to pass through them. They are fragile, fleeting doorways, shortcuts across the cosmos that exist more firmly in our calculations than in our reality. Black holes can spin at near the speed of light. When a massive star collapses, it retains its angular momentum. Just as an ice skater spins faster when they pull their arms in, the black hole spins incredibly fast as its mass becomes concentrated into a tiny point. Some black holes have been measured to be spinning at over 90% the speed of light at their event horizon. This rapid spin profoundly twists the space-time around it, creating the ergosphere and storing a truly colossal amount of rotational energy. It is a cosmic dynamo, a spinning top of infinite density, turning with a speed that bends the universe around it. Black holes can grow by merging with other black holes. When two galaxies collide, their central supermassive black holes will inevitably begin a long, slow dance. Over millions of years, they orbit each other, gradually drawing closer as they shed energy in the form of gravitational waves. Eventually, they merge in a final cataclysmic event. The two event horizons join to become one, creating a single, more massive black hole. This is how the supermassive black holes are thought to have grown so large, by consuming their kin, a quiet, gravitational cannibalism that builds the giants of the universe. The merger of black holes creates gravitational waves. When two massive objects like black holes spiral into each other, their dance disturbs the fabric of space-time, sending out ripples of gravity that travel across the universe at the speed of light. These are gravitational waves. In the final moments of the merger, this chirp of gravitational waves is incredibly powerful, briefly releasing more energy than all the stars in the observable universe combined. But it is a silent power. The waves pass through matter without a trace, a ghostly storm in the fabric of reality itself, the final echo of a colossal embrace. Gravitational waves were first detected in 2015. a century after Einstein predicted them. The Laser Interferometer Gravitational Wave Observatory, or LIGO, made history. On September 14, 2015, its two detectors, separated by thousands of miles, both registered the faint, unmistakable chirp of two black holes merging. The signal had traveled for over 1 billion years to reach us. This detection was a triumph, opening an entirely new window onto the cosmos. For the first time, we were not just seeing the universe, we were listening to it, hearing the faint drumbeats of space-time itself. The photon sphere is where light can orbit a black hole. Outside the event horizon, there is a region called the photon sphere. At this precise distance, gravity is so strong that photons, particles of light, can be forced to travel in orbits. A beam of light could, in theory, circle the black hole forever, trapped in a gravitational loop. If you were to stand in this photon sphere and look forward, you could theoretically see the back of your own head as the light from your body travels all the way around the black hole and back to your eyes. It is a ring of captured light, a halo of pure energy held in a perfect gravitational orbit. Black holes may be surrounded by dark matter. Dark matter is the invisible, mysterious substance that makes up about 85% of the matter in the universe. We cannot see it, but we know it is there by the gravitational pull it exerts on stars and galaxies. Because dark matter interacts with gravity, it should also be drawn toward black holes. Over eons, a halo or a dense spike of dark matter may accumulate around a black hole, feeding it and adding to its mass. The black hole's event horizon may be shrouded in an invisible cloud of this exotic substance, a dark heart within a darker veil. Rogue black holes may wander the galaxy. When a supernova creates a black hole, the explosion is not always perfectly symmetrical. The blast can give the newborn black hole a kick, sending it flying through space at incredible speeds. It is estimated that there could be millions of these rogue or wandering black holes moving silently through the Milky Way, unattached to any star system. They are invisible, detectable only if they happen to pass in front of a distant star, their gravity briefly bending its light. They are the galaxy's quiet nomads, dark pilgrims on an endless unseen journey. A star can be torn apart by a black hole. If a star wanders too close to a supermassive black hole, the tidal forces can overwhelm the star's own gravity. The side of the star closer to the black hole is pulled so much more strongly that the star is ripped apart into a long, glowing stream of gas. This event is called a tidal disruption. Some of this gas is flung out into space, while the rest forms a brilliant accretion disk, feeding the black hole and causing it to light up in a flare of X-rays. It is a star's final luminous cry, as it is unraveled by the patient, overwhelming power of gravity. Micro black holes are a theoretical possibility. Some theories of physics, such as those involving extra dimensions, suggest it might be possible to create microscopic black holes. If these theories are correct, high-energy particle collisions, like those at the Large Hadron Collider, could potentially create them. However, these tiny black holes would be utterly harmless. They would evaporate almost instantly via Hawking radiation, disappearing in a tiny puff of energy in less than a septillionth of a second. They would be the briefest of shadows, existing for less than a moment before dissolving back into the light. The first black hole candidate was found in our cosmic backyard. A black hole known as V616 Monocerotis, or A0620-00, is one of the closest known black holes to Earth, at a distance of about 3,000 light-years. It is part of a binary system, where it pulls material from a companion star. This companion is a small orange dwarf, and as the black hole strips away its outer layers, the material forms a bright accretion disk. This system gives us a relatively close-up view of how a stellar mass black hole interacts with its neighbor, a quiet, gravitational relationship unfolding just down the street in galactic terms. Black holes are essential for galactic recycling. The colossal jets of energy fired from supermassive black holes do more than just stop star formation. They blast heavy elements forged inside stars and supernovae, far out of the galaxy's core and into the intergalactic medium. This material then cools over billions of years and can eventually fall back onto the galaxy, or onto neighboring galaxies, providing the raw material for new generations of stars and planets. The black hole acts as a great cosmic fountain, ensuring that the building blocks of life are not locked away, but are shared across the cosmos. Black holes have a maximum spin rate. While black holes can spin incredibly fast, they do have a limit. A theoretical maximum spin exists, known as the extremal limit. If a black hole were to spin any faster than this, its event horizon would be forced to spin faster than the speed of light, which is forbidden. At this maximum speed, the event horizon would vanish entirely, exposing the singularity to the universe in what is called a naked singularity. Most physicists believe a law of cosmic censorship prevents this, ensuring that all singularities remain decently veiled behind the one-way door of an event horizon. The sound of a black hole has been recorded. In 2003, astronomers studying the Perseus galaxy cluster detected pressure waves or sound waves rippling through the hot gas that fills the cluster. These waves were being generated by the supermassive black hole at the cluster's center, which was sending out jets of energy. The note being played was a B-flat, but it was 57 octaves below middle C, a frequency so low that one oscillation takes about 10 million years. Scientists were able to scale this up into the human hearing range, allowing us to listen, for the first time, to the slow, deep, gravitational hum of a black hole. You can't see inside a black hole, but we can model it. If one were to cross the event horizon, our current theories suggest the journey would be a strange one. Space-time becomes so warped that, for a stellar mass black hole, you would be destroyed by tidal forces before you even reach the center. For a supermassive black hole, the tidal forces at the horizon are gentle, and you could cross without noticing. Once inside, all paths, all possible directions, would lead only to the singularity. The flow of time itself would become a river pulling you inevitably toward that single, infinitely dense point at the center of the dark. The accretion disk is a river of light. This glowing, flat disk of gas and dust is not part of the black hole itself, but is material that has been captured by its gravity. As this matter spirals inward, it doesn't fall straight in. It orbits, like water circling a drain. The atoms of gas and dust rub against each other at incredible speeds, and this immense friction generates heat, causing the disk to glow brighter than 1,000 suns. It is a celestial sawmill, a place where matter is ground down by gravity, releasing its stored energy as a final brilliant blaze of light before it crosses the quiet threshold of the horizon. A black hole has a temperature. While a black hole itself is cold and dark, Stephen Hawking showed that its event horizon radiates energy. This Hawking radiation gives the black hole an effective temperature. This temperature is inversely proportional to its mass, meaning that larger black holes are actually much colder than smaller ones. A stellar mass black hole would have a temperature just a fraction of a degree above absolute zero, far colder than the background chill of space itself. It is a quiet, almost imperceptible warmth, the faintest breath from the edge of the void. Smaller black holes evaporate faster. The rate at which a black hole evaporates via Hawking radiation depends on its size. A large, supermassive black hole is so cold that it absorbs more energy from the cosmic background radiation than it emits, so it will actually continue to grow. However, a very small black hole would be incredibly hot and would radiate energy at a furious pace. A black hole with the mass of a mountain, perhaps formed at the dawn of time, would evaporate in a bright flash of energy. The smaller the shadow, the more desperately it radiates, eager to return its borrowed mass to the light. The shadow of a black hole is larger than its event horizon. The shadow we see in images, like the one of M87, is not the event horizon itself. It is a region about 2.5 times larger, created by the black hole's extreme gravity. This shadow is formed by the photon sphere, that region where light is forced to orbit. The inner edge of this light ring marks the boundary of all captured light paths. The dark region inside is the silhouette of the black hole, a gravitational shadow cast against the backdrop of the glowing gas, a dark pupil in a fiery cosmic eye. Black holes can flicker on a timescale of minutes. The supermassive black hole at the center of our galaxy, Sagittarius A star, is a sleeping giant. While it is mostly quiet, astronomers have observed it flaring up brightly in X-rays and infrared light. These flares, which can last for an hour or so, are thought to be caused by small clumps of gas, or perhaps an unlucky asteroid, being torn apart and consumed by the black hole. It is the sound of the giant stirring in its sleep, a brief flicker of activity that reminds us of the immense, quiet power resting at the heart of our galactic home. The Eddington limit is a black hole's feeding limit. A black hole cannot consume matter infinitely fast. As material falls into the accretion disk, it heats up and radiates intense light. This light, in the form of photons, carries momentum and pushes outward. This is known as radiation pressure. If a black hole tries to eat too quickly, this outward pressure of light becomes so strong that it will actually halt the inflow of gas, blowing it back into space. This natural feedback loop, the Eddington limit, acts as a cosmic regulator, ensuring the black hole's meal is taken at a suikumura, measured and sustainable pace. Black holes can be electrically charged. While most black holes are thought to have a neutral charge, the no-hair theorem allows for them to carry a net electric charge. This would happen if the matter that collapsed to form it, or the matter it consumed, had more of one type of charge, like protons, than the other, like electrons. A charged black hole would have slightly different properties, its gravity and electromagnetism intertwined. However, it is believed that any charge would be quickly neutralized as the black hole preferentially pulls in oppositely charged particles from the surrounding space, returning to a state of quiet electrical neutrality. Black holes are part of the cosmic web. On the grander scales, the universe is structured like a three-dimensional web, a vast frothy network of filaments made of gas and dark matter, separated by immense voids. Galaxies are not scattered randomly, but are instead strung along these filaments, like pearls on a string. The supermassive black holes grow by feeding on the cold streams of gas that flow along these cosmic highways, funneling material toward the galactic centers. They are the great gravitational spiders sitting at the intersections of this vast, invisible web, patiently drawing in the sustenance of the cosmos. Blazes are black hole jets pointed directly at us. Some active galaxies, or quasars, shoot out jets of high-energy particles at nearly the speed of light. In a rare alignment, sometimes one of these jets is aimed almost perfectly at the Earth. When this happens, we call the object a blazar. Because the jet is moving toward us so fast, its light is dramatically brightened and intensified by relativistic effects. We are staring, in effect, directly down the luminous barrel of a galactic engine. It is one of the most energetic and dramatic sights in the universe. A cosmic lighthouse beam sweeping across the void and shining directly into our eyes. The membrane paradigm reimagines the event horizon. To an outside observer, nothing ever truly crosses the event horizon. It just seems to slow down and freeze at the edge. To simplify the complex physics, some physicists treat the event horizon as if it were a real physical surface, a membrane. They imagine it as a two-dimensional surface with properties like electrical conductivity and viscosity. This is a mathematical tool, a way of translating the strange laws of relativity into a language we can more easily understand. It allows us to calculate and dream about the horizon, treating it not as a bottomless pit, but as a strange, fluid skin on the surface of space-time. Information may be stored on the event horizon. The information paradox asks what happens to the story of an object that falls in. One proposed solution is the holographic principle. This idea suggests that all the information about the three-dimensional object that fell in is not destroyed, but is instead encoded and stored on the two-dimensional surface of the event horizon, like a complex hologram. As the black hole evaporates, this information is slowly and subtly imprinted onto the outgoing Hawking radiation, to be released back into the universe. The black hole becomes a cosmic scribe, meticulously recording every detail of what it touches on its ever-shrinking skin. The universe may end in a black hole era. If the universe continues to expand forever, we may one day enter the black hole era. In the far, far future, trillions of years from now, all the stars will have burned out. The galaxies will be dark, populated only by cold stellar remnants and black holes. These black holes will be the only active objects in the cosmos, slowly consuming the frozen cinders of dead stars. They will be the last points of gravity, the last active engines in a cold and dying universe, the quiet rulers of the endless night. After the black hole era comes the dark era. The reign of the black holes is not eternal. After an unimaginable timescale, so long that the human mind cannot grasp it, even the most supermassive black holes will have finally evaporated, dissolving into a faint bath of Hawking radiation. With their passing, the universe will enter its final stage, the dark era. There will be no more organized matter, no stars, no black holes, only a diffuse cold soup of elementary particles and photons, drifting ever further apart in the accelerating expansion. It is the ultimate quiet end, a state of perfect peaceful entropy. The final pop of a black hole. As a black hole evaporates, its temperature and radiation rate increase. In its very final moments, a small, mountain-sized black hole would become incredibly hot. It would release its remaining mass in a final, sudden burst of high-energy gamma rays and particles. This pop would be the black hole's last, brief testament, a final spark as its event horizon vanishes and its singularity is released. For a stellar mass black hole, this process is so slow that its final moment will not come for a time longer than all the ages of the current universe combined. Black holes are connected to the arrow of time. Why does time only move forward? This is one of physics' deepest questions. Some theorists connect this to the growth of black holes. The universe began in a smooth, low-entropy state, and black holes are objects of maximum entropy or disorder. The arrow of time may be driven on the universe's inexorable journey toward higher entropy, a journey dominated by the formation and growth of black holes. They are the engines of entropy, the gravitational force that pulls the cosmos forward from its simple past toward its complex and disordered future. Black holes can be formed without a star. In the dense, chaotic cores of globular clusters, where hundreds of thousands of stars are packed tightly together, a black hole can be built. In this environment, stellar collisions are common. Stars can merge, growing larger and larger, or multiple dead stars like neutron stars can spiral together and merge, their combined mass great enough to collapse into a stellar mass black hole. This is a different kind of birth, not from the death of one great star, but from the union of many smaller, dense remnants, a quiet assembly in the heart of a stellar swarm. The first theorized black hole was a dark star. In 1783, long before Einstein, the geologist John Michell proposed a fascinating idea. He reasoned that if a star were massive enough, its gravitational pull could be so strong that its own escape velocity would be greater than the speed of light. He called this a dark star. He correctly predicted that we would be unable to see it, but we could detect its presence by observing its gravitational pull on a nearby luminous companion star. It was an astonishing piece of insight, a seed of an idea that would lie dormant for over a century, a premonition of the great shadows we were yet to discover. Black holes can create bubbles in space. The powerful jets fired from supermassive black holes do not just travel in a straight line. They carve out immense cavities in the hot gas that surrounds their host galaxy. These bubbles, which can be larger than entire galaxies, are filled with high-energy particles and magnetic fields. We can see them in X-ray and radio telescopes. Vast, empty regions where the black hole's energy has pushed the intergalactic medium aside. They are the long-lasting, visible breath of the black hole, a testament to the power that has been shaping the galaxy over millions of years. Sagittarius A star is starving. For a supermassive black hole, the heart of our Milky Way is remarkably peaceful and dim. Its quiescence is a mystery. It is surrounded by stars and gas, yet it consumes very little. One theory is that the gas in the galactic center is too hot and diffuse to be easily captured. Another is that magnetic fields are acting like a shield, diverting the flow of gas away from the black hole's event horizon. Our central giant is on a cosmic diet, a sleeping dragon that, for now, lets the matter of the galaxy drift by in peace. Black holes may be the source of fast radio bursts. Fast radio bursts, or FRBS, are intense, millisecond-long flashes of radio waves that come from deep space. Their origin is one of the biggest mysteries in modern astronomy. One compelling theory suggests they may be connected to young, highly magnetized black holes. Or they could be the final pop of an evaporating primordial black hole. These brief, powerful signals from across the cosmos may be the whispers or cries of black holes, a new language they are using to speak to us from the darkness, the innermost stable circular orbit. Outside the photon sphere, there is another critical boundary, known as the ISCO, or the innermost stable circular orbit. This is the last orbit where an object, like a planet or a star, can circle the black hole in a stable path, just as the Earth orbits the Sun. Any object that drifts inside this line will no longer be able to maintain a stable orbit. Its path is doomed to decay, and it will begin an inexorable, gentle spiral inward to be inevitably consumed by the black hole. It is the final, stable shoreline before the gravitational river begins to flow in only one direction. Black holes are cold on the outside, while the accretion disk, the material falling into a black hole, is one of the hottest places in the universe. The black hole itself is one of the coldest. The event horizon of a stellar mass black hole has a temperature, due to Hawking radiation, that is just a whisper above absolute zero. This is far colder than the 2.7 Kelvin background temperature of empty space. This means that, in our current universe, all stellar and supermassive black holes are actually absorbing more energy from the cosmic background than they are emitting. They are, for now, getting colder and heavier, not warmer and smaller. Black hole bombs are a theoretical concept. A spinning black hole's ergosphere, the region where it drags space-time, offers a curious possibility. If a field of reflective particles, like a mirror of light, could be placed around the black hole, any light that entered the ergosphere could be amplified. The light would gain energy from the black hole's spin, bounce off the mirror, and re-enter the ergosphere to be amplified again. This process, called super-radiant scattering, would create a bomb of light, exponentially growing in power by drawing it from the black hole's spin. It is a thought experiment that reveals the vast, accessible energy locked within a spinning void. Black holes are the simplest objects in the universe. The no-hair theorem, which states a black hole only has mass, charge, and spin, makes them fundamentally simple. A star is a complex object, a swirling ball of plasma with a complex chemical composition, magnetic fields, and turbulent layers. When it collapses, all of this complexity is smoothed away. The resulting black hole is a perfect, clean object, a pure manifestation of gravity. It is as if the universe, in its most extreme state, seeks a return to simplicity, erasing all the messy details and leaving only a smooth, dark, and perfect shadow. The inside of a black hole might be a new universe. What happens at the singularity, that point of infinite density? Our current physics breaks down, but some theories propose a radical answer. Instead of a crushing point, the collapse might bounce and create a new Big Bang, forming an entirely new, expanding universe inside the black hole. In this black hole cosmology model, our own universe might be the interior of a black hole that exists in a larger parent cosmos. It is a grand, recursive idea, a cosmic nesting doll where every dark heart is a potential new beginning. Black holes can be kicked out of their own galaxies. When two supermassive black holes merge, the event is incredibly violent, releasing more energy in gravitational waves than all the stars in the universe. If this emission of energy is not perfectly symmetrical, if more waves are blasted in one direction than another, it creates a recoil. This recoil acts like a rocket engine, and it can be powerful enough to kick the newly merged giant black hole, sending it flying out of its host galaxy's core. It could be sent into the galaxy's halo, or even ejected entirely into the lonely void between galaxies, a titan exiled from its own kingdom. Black holes can imprint their spin on their jets. The powerful jets of energy launched from a black hole's poles are not just random blasts. They are shaped and guided by the black hole's own rotation. The black hole's spin twists the magnetic fields in the accretion disk, wringing them out like a wet towel. This process shapes the outflowing material into a tightly focused, high-speed beam. The jet, therefore, carries a memory of the black hole's spin, a long-range, visible testament to the rotational power of the unseen engine that launched it billions of light years across the cosmos. Black holes have a ring-down phase. After two black holes merge, the new, larger black hole is temporarily misshapen, wobbling and vibrating like a struck bell. It quickly settles down into a perfect, stable, no-hair state. As it does, it radiates away these imperfections as a final burst of gravitational waves. This is the ringdown. The specific frequencies and decay of this ringdown are a pure signature of the new black hole's mass and spin. Listening to this celestial chime, as LIGO does, is like hearing the final clear note of a bell that has been struck, confirming the birth of a new quiet giant. The nearest black hole is surprisingly close. For a long time, the closest black hole was thought to be thousands of light years away, but recent observations have identified candidates much closer. One, named the Unicorn, is a mere 1,500 light-years distant. It is a small, stellar mass black hole, only about 3 times the mass of our Sun, locked in a dance with a red giant star. Its proximity is a quiet reminder that these exotic objects are not just in distant galaxies. They are our neighbors, part of the local fabric of our own small corner of the Milky Way. The cosmic censorship hypothesis protects us from singularities. The singularity at the center of a black hole is a place where physics breaks down. What would happen if one could exist without an event horizon to hide it? This is a naked singularity, and it would be a chaotic, unpredictable object, spitting out random effects and violating the laws of causality. The physicist Roger Penrose proposed the cosmic censorship hypothesis, which suggests that the laws of physics themselves forbid this. It is a cosmic rule of modesty, ensuring that all singularities are always and forever clothed by the decent, one-way veil of an event horizon. Black holes are not dark in every spectrum. While they are black in visible light, black holes are some of the brightest objects in the universe in other wavelengths. The superheated material in their accretion disks shines intensely in X-rays and gamma rays. The powerful jets they launch are vast and luminous in radio waves. When we build telescopes that can see in these other colors, the dark void becomes a blazing beacon. The black hole's shadow is only visible because it is cast against a backdrop of such immense high-energy light, a light generated by its own gravitational power. The spin of a black hole can be measured. We can determine how fast a black hole is spinning by looking at its accretion disk. The intense gravity and spin of the black hole warp the light coming from the disk. Specifically, it smears the X-ray light in a very particular way, a relativistic effect known as broadening. By analyzing this smeared light, astronomers can calculate the spin of the black hole's event horizon. It is a remarkable feat, a way of measuring the motion of an invisible edge by watching the distortion of the light that dances just outside it. A black hole's mass determines its size. The size of a black hole's event horizon, its radius, is directly proportional to its mass. This is called the Schwarzschild radius, If our sun were to become a black hole, its event horizon would be only about 3 kilometers across. If the Earth were to collapse into a black hole, it would be the size of a small marble. A supermassive black hole, billions of times the mass of our sun, would have an event horizon large enough to swallow our entire solar system. They are perfect spheres, their size a pure and simple measure of the mass they quietly contain. Black holes have bald spots. While the no-hair theorem states black holes are simple, some recent theories suggest they might have a little fuzz. Quantum effects near the event horizon might allow for very subtle, low-energy fields to persist, like soft hair. This is a highly theoretical idea, an attempt to solve the information paradox. It suggests that the black hole might retain a faint, quantum memory of what it swallowed, a ghost of its past imprinted on the very edge of the horizon. It is a way of giving the void a faint, shimmering, and informative glow. Black holes may be fuzzballs instead of singularities. String theory, an attempt to unite all physics, offers a radical alternative to the black hole. In this fuzzball model, there is no singularity and no true event horizon. Instead, the entire region is a tangled, vibrating ball of fundamental strings. From the outside, it would look and act exactly like a black hole. But on the inside, it would be a solid, albeit strange, object. Information would not be destroyed, but would be stored in the complex vibrations of the strings. The black hole would no longer be a pit, but a dense, cosmic ball of yarn. The color of an accretion disk reveals its temperature. Like a piece of metal heated in a forge, the color of the accretion disk tells us its temperature. The outer, cooler parts of the disk, where friction is less, glow in the red and infrared. As the material spirals closer to the event horizon, it gets hotter and hotter, glowing white hot, and then blazing in the high-energy X-ray spectrum. By observing this rainbow of heat, astronomers can map the disk's structure and understand the flow of matter as it makes its final luminous journey toward the black hole's edge. Black holes are the universe's most efficient engines. A black hole's accretion disk converts mass into energy with terrifying efficiency. A nuclear fusion reaction, like the one that powers our sun, converts only about 0.7% of mass into energy. But the friction and gravitational energy in an accretion disk can convert 10, 20, or even up to 40% of an object's mass into pure radiation. This is what makes quasars so bright. A black hole is the ultimate gravitational engine, a perfect machine for turning matter into light. Black holes can have magnetic fields, while a black hole itself, according to the no-hair theorem, cannot have its own magnetic field. The accretion disk around it most certainly does. As the conductive plasma of the disk spins, it generates an incredibly powerful and complex magnetic field. These field lines are thought to be the scaffolding that shapes and launches the jets. The black hole's spin twists these fields, creating a magnetic tower that can funnel particles and energy outward, away from the black hole and across the galaxy. The cosmological constant was inspired by black hole physics. When Einstein first created his equations, they implied the universe must be expanding or contracting. He added a cosmological constant to make it static. But black hole thermodynamics in the 1970s showed that black hole entropy was related to the area of the event horizon. This idea, along with other discoveries, resurrected the cosmological constant as a real physical property, which we now know as dark energy. The quiet study of black hole shadows helped lead us to the profound discovery that our entire universe is accelerating in its expansion. Black holes are places where time and space swap roles. Inside the event horizon, the warping of space-time becomes so extreme that our normal reality is turned on its head. For an object inside, the spatial direction toward the singularity becomes its future. It is no longer a place you can go, but an event in time that you must meet. And the timed dimension, which always moves forward, becomes like a spatial direction. All paths, all movements, must move toward the singularity, just as we, in our normal lives, must always move forward into tomorrow. It is the ultimate transformation, where space becomes time, and the center is no longer a place, but an inevitability. Gravitational redshift is the stretching of light. As light climbs out of a black hole's intense gravitational well, it must expend energy. This causes its wavelength to be stretched, shifting it toward the red end of the electromagnetic spectrum. A blue hot photon leaving the vicinity of the event horizon would arrive at a distant observer as a faint, cool red photon. If it were to be emitted from the event horizon itself, it would be stretched to an infinite wavelength, carrying no energy and becoming undetectable. It is the light's long, quiet sigh, a final exertion as it pulls away from the grip of gravity to continue its cosmic journey. Frame dragging is the twisting of space. A spinning black hole does not just curve space-time, it actively drags it along in its rotation. This is the lens-thurrying effect. Imagine a spinning ball dipped in honey. The honey closest to the ball is dragged along with it. In the same way, the very fabric of space and time is forced to swirl around a rotating black hole. Any object, even a beam of light, that enters this region is forced to co-rotate, its path twisted by the black hole's immense spinning wheel. It is the universe caught in a gentle gravitational vortex, a waltz for planets and light itself. Black holes can suppress star formation. The powerful jets and winds that blast from a supermassive black hole's accretion disk are a form of negative feedback. They inject vast amounts of heat and energy into the surrounding galactic gas clouds. This heating prevents the gas from cooling and collapsing under its own gravity, which is the necessary first step in forming new stars. The black hole acts as a cosmic thermostat, ensuring the galaxy does not burn through its creative fuel too quickly. It is a form of galactic conservation, a quiet, not yet, whispered to the stellar nurseries. Sagittarius, a star, had a close call with a gas cloud. In 2014, astronomers watched in anticipation as a mysterious gas cloud named G2 passed perilously close to our galaxy's central black hole. Many expected the cloud to be torn apart by tidal forces, triggering a spectacular flare-up as it was consumed. Instead, the cloud seemed to largely survive its passage, stretching and elongating, but mostly staying intact. This anticlimax was itself a profound lesson, teaching us about the complex, magnetized environment at our galaxy's heart, a place where even a giant's meal can be complex and unpredictable. The smallest possible black hole is a Planck mass. In the realm of quantum gravity, there is a theoretical smallest mass, the Planck mass, which is about the mass of a flea's egg. A black hole with this mass would be the smallest possible, with an event horizon only a Planck length across, the fundamental, indivisible unit of space. This tiny object, a quantum black hole, would be incredibly hot and would evaporate via Hawking radiation almost instantly, in a time so short, it is almost meaningless. It represents the very boundary where gravity, quantum mechanics, space and time all merge into one single fundamental mystery. The firewall paradox is a modern cosmic puzzle. The information paradox led to a deeper problem. If information is encoded on the event horizon, as the holographic principle suggests, what happens to an astronaut crossing it? Quantum mechanics implies they should pass through unharmed, but other principles suggest that to handle the information, the horizon must be a high-energy firewall, incinerating anything that touches it. This contradiction has physicists deeply puzzled, suggesting a profound misunderstanding of how space-time works at its most fundamental level. The event horizon remains a gentle-looking door that may hide a fiery, paradoxical secret. The black hole echo may reveal its true nature. Some alternative theories to black holes, like fuzzballs or objects with a real surface, suggest that an event horizon is not a one-way door. If this is true, when two black holes merge, the gravitational waves might not just fade away. A tiny fraction of the waves could be reflected off this exotic surface, creating a faint echo that arrives just after the main signal. Scientists are now carefully listening to the LIGO data, searching for these quiet, ghostly reverberations that could tell us if the void has a flaw. The shadow of a black hole is a perfect test of relativity. Einstein's theory of general relativity makes a very specific prediction about the size and shape of a black hole's shadow. The image of M87's shadow, that perfect dark circle against the glowing gas, was a profound confirmation. Its size and shape matched the predictions of general relativity with beautiful precision. Had the shadow been a different shape or a different size, it would have been the first sign that Einstein's theory was incomplete. Instead, the shadow stood as a silent, perfect monument to a theory that described it a century before it was ever seen. Black holes as dark matter are an old idea. Could the dark matter that holds our galaxy together simply be a vast swarm of ancient, primordial black holes? This was once a leading theory. These objects would be massive but invisible, perfectly matching the description of dark matter. However, recent observations, particularly of gravitational lensing, have put tight constraints on this. It seems there simply are not enough of them in the right mass ranges to account for the missing mass. The dark matter remains a deeper mystery, a substance more ethereal than even the shadows themselves. The black hole chirp is a sound of space-time. When the LIGO detectors first heard the merger of two black holes, the signal was translated into sound. It was a brief, rising chirp, the frequency sweeping upward in less than a second as the two objects spiral faster and faster, closer and closer together. This sound was the literal vibration of space-time itself, a wave of gravity washing over the Earth. It was the universe's own song, a note played on the fabric of the cosmos, the final harmonic chord of a billion-year dance. A black hole remnant may solve the information paradox. What is left when a black hole evaporates? One idea is that the evaporation stops when the black hole reaches the tiny quantum Planck mass. At this point, it could become a stable, microscopic remnant, a tiny, inert particle that no longer radiates. This remnant would contain all the information of the original massive star it came from, locked away in a tiny quantum vault. The universe would be filled with these information-rich seeds, the quiet, final ashes of long-dead stars and their gravitational hearts. Black hole factories exist in globular clusters. Globular clusters are ancient, dense cities of stars. With so many stars in such a small space, interactions are common. This environment is a perfect factory for black holes. Not only are they born there, but they quickly sink to the center of the cluster. In this dense central core, they can find each other, merge and grow, forming the intermediate mass black holes that are so rare elsewhere. The cluster's heart becomes a quiet, gravitational forge, building ever larger shadows from the remnants of its oldest stars. Looking out from near a black hole distorts the universe. If you were to hover just outside the event horizon, the view would be extraordinary. The black hole's gravity would bend the light from the entire universe. The sky would be compressed into a small, bright circle of light in one direction. Looking forward, you would see the entire cosmos, the distant galaxies and stars, all warped and distorted in a small circular window. In all other directions, you would see only the perfect, quiet blackness of the event horizon. It is a view from the edge of reality, where all of starlight is gathered into a single celestial eye. The M87 black hole is unimaginably large. The supermassive black hole at the heart of the M87 galaxy, the one we first imaged, has a mass of 6.5 billion suns. Its event horizon, the shadow we see, is larger than our entire solar system. If it were placed at the center of our galaxy, it would extend beyond the orbit of Pluto. It is a true titan, a gravitational well so vast that it holds an entire galaxy of hundreds of billions of stars in its gentle, massive embrace. It is a quiet mountain in the center of a cosmic kingdom, a shadow that outweighs worlds. A spin-R is a theoretical alternative to a black hole. What if the collapse of a star never forms an event horizon? One alternative model is the spin-R, or a magnetospheric eternally collapsing object. This theory suggests that the collapsing object forms an incredibly strong magnetic field, which halts the collapse just before an event horizon can form. The object would be a spinning, ultra-dense ball of plasma, just barely larger than its own Schwarzschild radius. From a distance, it would look almost identical to a black hole, but it would have a hard surface, a place where information and matter could rest, rather than a one-way door. Black holes scramble information. Even if information is not destroyed, it is certainly scrambled. Physicists believe that a black hole is a fast scrambler, meaning it takes any information that falls in and almost instantly mixes it into a complex, encoded state across the entire event horizon. A single book falling in would have its information smeared across the horizon in a way that would be, for all practical purposes, impossible to read. The black hole acts as the ultimate encryptor, taking every secret of the universe and locking it in a code so complex that it may never be broken. Black holes may be connected to cosmic inflation. The theory of cosmic inflation states that in the first fraction of a second, the universe expanded faster than the speed of light. This rapid stretching is what made the universe so large and smooth. What drove this? Some physicists propose that the universe could have been born from a black hole in a higher dimensional space. The mathematics describing the birth of our universe and the formation of a black hole are strikingly similar. Our entire cosmos, in this view, may be the result of a process that, in another reality, simply formed a quiet gravitational shadow. The inner horizon is a path to the past. According to the mathematics of a spinning, or Kerr, black hole, the singularity is not a point, but a ring. The theory also predicts that past the main event horizon, there is a second inner horizon. If one could pass through this inner horizon, The laws of physics suggest you would enter a bizarre region where causality is violated, and you could, in theory, travel into the past or into other universes. However, this is almost certainly a mathematical fantasy, as physicists believe this inner horizon would be lethally unstable, a doorway that collapses in a blaze of energy before anything could ever pass through. Black holes are the final archives. In the far, far future, when all stars are dead and all energy has dissipated, the black holes will remain. They will be the last massive organized objects in a cold, dark, and empty universe. For eons, they will hold within them the compressed matter of entire galaxies, the scrambled information of dead civilizations, the final remnants of suns and planets. They will be the universe's silent libraries, the last quiet monuments to all that ever was, before they too, in their turn, slowly dissolve and give their stories back to the void. The event horizon is a philosophical boundary. The event horizon is more than a physical place. It is a concept. It is the border between the known and the unknowable, the reachable and the forever lost. It represents a boundary in our understanding, a place where our most trusted theories, relativity, and quantum mechanics meet and disagree. To study the black hole is to study the limits of our own knowledge, to stand at the shore of a dark, quiet ocean and wonder at the mysteries that lie just beyond our sight. It is a final, gentle reminder from the cosmos that there are, and always will be, frontiers beyond our grasp. And so, our journey through the shadowy world of black holes comes to a gentle close. We have drifted by the event horizon, that quiet shore where time and space curve into a final, peaceful mystery. We have wondered at the great sleeping giants at the hearts of galaxies, those silent anchors that hold the stars in their long, slow dance. The singularity, the paradox, the echo of gravitational waves, these are concepts of profound cosmic awe. They are the universe at its most extreme, its most simple, and its most grand. The black hole is the final, dark repository of starlight, a place where matter returns to its simplest form. It is the universe's quietest engine and its most patient archive. The mysteries we have touched upon tonight are the deep, restful thoughts of the cosmos itself, a reminder of the vast, silent elegance that governs all things, from the smallest particle to the grandest shadow. If you happen to still be awake, that's just fine. The story will still be here when you wake, patient and timeless. But if your eyes are heavy, let the stories of black holes carry you gently into rest. Sleep well. Good night.